Hi everyone, thank you for coming to our presentation on post-quantum cryptography. I'm Danica Cariaga.
And I'm Amber Thomas.
So to get started, Amber, will you lead us?
Yes, so this picture here, why we're talking about post-quantum cryptography, is a picture of why we are here, because of quantum computers. So for background, quantum computers are machines that are based off of quantum physics. So they can actually have more than one state of being, but you can only have one result. So it's similar to the Schrodinger's cat, where the cat can be both dead and alive, but once it's viewed, it can either be dead or alive. And we can relate that with binary numbers of zeros and ones of being in multiple states. This means it can compute many streams of data at once. And because of this, the Shor's algorithm, which we'll go into detail a little bit more throughout the presentation, would be able to effectively crack the ubiquitous RSA encryption algorithm. So quantum computers, they are on track to break our current encryption algorithms. They do speed up super polynomially. So that means we would need strong encryption standards that are necessary to protect our data. So cracking our current classical computer algorithms with quantum computers, all of our private data, they will be exposed. So the RSA using Shor's algorithm has already proven that it's able to crack the RSA code.
Okay, so in depth, we have our challenges. The first one is Shor's algorithm, and then the data harvesting and migration time. So Shor's algorithm essentially is a quantum algorithm in polynomial time, and it's used for integer factorization, and it's the current standard for quantum computational effectiveness. Data harvesting, which is our other challenge, is when we have our current encrypted data with used encryption such as RSA or DES and AES, and those are currently being collected to be cracked with quantum computers in the future. And then the last challenge is our migration time. So as you know, our post-quantum cryptographic standards have not yet been solidified. So migration time will take a long time and in fact use a lot of resources, just as a note. And that cost is relevant to both the time and money that it will take to have all of that done. And so moving on.
So for a perspective of processing times for bits versus qubits, we'll use the RSA encryption algorithm as an example again. So for a 248-bit digital key with the RSA encryption, it would take a classical computer about 300 trillion years to crack. But with a quantum computer with 4099 qubits, it would take only about 10 seconds. So another thing that could harden the hardware-oriented cryptography would be a distributed web system. So these networks would allow for effective hardware systems that can be a more secure approach to quantum authentication. So with a qubit level encryption, which is similar to what's deployed using cryptographic hashing, would be possible with a distributed architecture. So quantum recursiveness can be used for recursive hashing in qubit-based processing that are interconnected in parallel. So that would add another encryption layer that can be more complex over time. Because qubits, they can be manipulated through high beam lasers and superconductivity. They can also be converted back to zeros and ones through polarized beams. So developing quantum recursive hashing and data encoding algorithms can allow for a multi-path layer level for cryptography on a hardware-oriented level.
Okay, and so next we have our National Institutes of Standards and Technology for post-quantum cryptography. Currently, as it's been previously stated, we are on the round 3 trials, and we have a proposed round 4 trial just because they're, pretty competitive. And so this selection of the process of selecting the post-quantum cryptographic standard will be solidified within the future to have this standardization. And the other big point to note are lattice-based cryptography used within post-quantum cryptographic standards. So basically, a lattice is a set of points in n-dimensional space. So it can be from 2-dimensional space to an infinite amount of dimensional space. And this lattices use a set of vectors. And within this set of vector, we have a pair, and one vector will be for the public key and the other vector will be for the private key. So it's very difficult to crack because we have the shortest vector problem. And going into that in more detail, let me show you this diagram. We have a figure of a lattice with the 2 possible bases. And so those 2 sets of vectors, we have the one going to the right would be considered a bad set of vectors because they're not the shortest possible, and then the one that's closer to the base going pretty much 1 point, those would be considered good vector sets. And so it's difficult to crack, but it's easy to implement and it's simple to understand, and lattice-based cryptography can be proven to be secure with its mathematical security proofs.
And from our recommendations, we propose a system that can be broken down into 3 categories to implement the migration now. So that would be discovery, implementation, and ongoing research. So right now, it's very important that we discover where current cryptographic instances are needed to be updated, replaced due to the quantum encryption cracking threat. So all guidances, standards, protocols, they must be reviewed to ensure that they will meet the post-quantum cryptography standards and protocols. It is essential that government agencies, other industries, and organizations are educated about the transition to post-quantum cryptography algorithms and how it affects their systems and assets. They need to review their cryptographic standards that are relevant to their specific activities. So once these activities have been discovered, they can work with standards organizations that have already developed methods or protocols or any updated methods that would prepare them for post-quantum computing migration. Then they would implement activities beginning with algorithms that identify sensitive information protected with cryptographic key establishments. So these algorithms, they're part of an automated tool that would inventory cryptographic usage by identifying hardware and software modules, libraries, and embedded code. It's important that they would prioritize the encrypted data based off of what was affected and their components and assets from that algorithm. Post-quantum cryptography implementation would then lead to real-world trials and testing of the modified systems using the NIST standards that are current, and right now they're currently on round 3. So that would be something that they could use now.
Okay, and then the last point, we have research. So research and collaboration has to be done with our existing infrastructure and existing research. And so what would be the main focus of it would be the differences in key and signature sizes, as well as memory and processing cycles and network latencies, as those all differ from our current encryption standards. Additionally, research would need to focus on cryptographic agility, as our post-quantum cryptographic standards would be used not just within that post-quantum era, but hopefully for decades and decades of future use. And lastly, we have to also take into account, research should look into key authentication and key management, as well as web, mobile, and IoT devices and their implementations. So for reference, here's a list of our sources. We would like to thank you for coming to our presentation and listening to what we have to say.
Thank you.